Right, guys. So we're going to go ahead and look at what happens whenever we mix acids and bases together. So some food for thought to think on of what happens whenever you mix an acid with an acid. Would they react with each other? So they would not actually react and negate each other, but instead, because they both have hydrogen ions, what would we expect to happen is we would expect the concentration of the acid to increase because their hydrogens are combining. So their hydrogen ion concentration is increasing. So we would expect the pH to decrease if we're mixing two acids together. But they're not chemically reacting and changing to neutralize one another. If we're mixing a base with a base, yet again, they would both be producing hydroxide in some form. So the concentration of the hydroxide would increase. They're not going to react to negate each other. So if there's more hydroxide, I'll put OH here, we would expect our pH to increase because there's more base overall when we're combining them. But if we have a mixture of an acid and a base, so you can think back to Unit 4, acids and bases react to produce water. So they will neutralize one another. So we would expect a neutralization reaction. And that is going to depend on how much acid and base react together. But what's going to end up happening typically is one of them will completely neutralize and we might have excess of the other one. So throughout the rest of this unit, we're going to be looking a lot at these acid-base mixtures, and we're going to look at what happens if we have two strong acids that are combining, if we have two strong bases that are combining, a strong acid and a strong base are combining, or what happens if we have like a strong acid and a weak acid, or a strong base and a weak base. Later this unit, we're going to look at what happens if we are doing one of those neutralizations where we have an acid and a base, but one of them is strong and one of them is weak. We are not going to look at what happens if we have two weak substances together, however. So the ones that we're going to look at soon are referred to as buffers. And you may have heard of buffers before in biology, or if you have taken anatomy, there are buffer systems in your body that you may have discussed. But we're going to look at those a little bit more in depth later on. And whenever we are dealing with the acids and bases combining, they are titration situations. So our buffers that we're going to look at are also the forms of titration. So what we're going to be looking at is what do we do with these mixtures? How do we know that the concentration changes and the pH changes? So if we're mixing similar solutions, so these are going to be when we're mixing two acids or two bases together. And then we're also going to look at what happens if we're mixing opposite solutions, so where we're mixing an acid and a base. With similar solutions, we have to find moles of the hydrogen or hydroxide from each solution, add the number of moles together to get the total moles that is being put in that beaker, and we have to find the new molarity, the new concentration, by dividing by the total volume. So this is similar to something that we did in solution stoichiometry, but we're adding our moles of acid to moles of acid and then dividing by the total volume. That would also work if we had two bases. And then we can find the pH in one or two steps by doing, if we are dealing with hydrogen ions, we can simply, once we get that new calculation or concentration, do the negative log of pH, or negative log of the hydrogen to get pH. If we have hydroxide ion concentration, we can solve for POH and then convert into pH. If we are mixing opposite solutions where we have moles of acid and base, we're going to find moles of hydrogen in our acid, moles of hydroxide in our base, and we are going to subtract them because they are going to cancel one another out. And you're always going to do like the higher one minus the lower one. And look at which one is left over. So that would determine if we have excess hydrogen or excess hydroxide that does not neutralize. Then the concentration is found by dividing that molarity, that number of moles, by the total volume to get the new molarity. And then yet again, we can plug in to solve for pH. But it all depends on whether we have excess hydrogen or hydroxide to if that's going to be a one-step calculation or a two-step calculation. So let's look at this in action. So looking at this example, here it says we have 20 milliliters of a 0.020 molar hydrochloric acid mixes with 25 milliliters of a 0.040 molar nitric acid. And if you look, hydrochloric acid is a strong acid. Nitric acid is also a strong acid. So remember, that means that these completely ionize. So we said we have to find moles of hydrogen for each of these. So if you remember, in terms of our molarity formula, if we're solving for moles, that is our molarity times our volume. And you do have to account for if there are multiple hydrogens that are in there. So looking at this for the hydrochloric acid, our molarity is the 0.020 molar. Our volume in liters is 0.020 liters. That gives us 4.0 times 10 to the negative fourth moles of hydrogen that are in hydrochloric acid. We have to do the same thing with the nitric acid. The molarity is 0.040 times our volume is 25 milliliters. That would be 0.025 liters. When we multiply, that is 0.001 moles of hydrogen. So we said we add those together. So that means that our total hydrogen is going to be 0.0014 moles. Now, to find our molarity, we said we take our number of moles and we divide by the total volume. So 20 milliliters plus 25 milliliters is 45 milliliters. So divide by the 0.045 liters. And that gives us our concentration of hydrogen, which is going to be equal to 0.031 molar hydrogen ions. Now, this would typically ask us for the pH. So in order to find pH, since we have H plus, we just have to do negative log of H plus, so our 0.031. And since our concentration has 2 sig figs, our pH should have 2 decimal points, so this would be 1.51. Now if we had looked at this individually, overall the combined amount, the pH would typically go down when we're mixing two acids together. Let's look at the next one. Here we have 40 milliliters of a 0.020 molar sodium hydroxide and 20 milliliters of a 0.040 molar calcium hydroxide that are added together. And so here, remember, sodium hydroxide is a strong base. Calcium hydroxide is also one of your strong bases. So these, it's the same type of substance. They're both bases, so they are going to add together. So we said whenever we're using similar substances, we have to find moles for each. So for sodium hydroxide, we said to find moles, you do the molarity times the volume. So it's 0.020 molar times 40 milliliters is 0.040 liters. So this would be 8.0 times 10 to the negative fourth moles of hydroxide. We need to do the same thing for the calcium hydroxide. And one thing to be careful of, calcium hydroxide, there are 2 hydroxides. So our number of moles multiplies by 2 automatically because of that subscript. So we did that when we did solution stoichiometry. We're still doing the molarity times the volume. So it is a 0.040 molar calcium hydroxide. There's 20 milliliters of that, so that's 0.020 liters. So that is 0.0016 moles of hydroxide. Since they are similar substances, we add them together. So that is a total of 0.0024 moles of hydroxide. We said to get the concentration, we divide by the total volume, which is 40 milliliters, and 20 milliliters is 60 milliliters. So that is a molarity of 0.040 molar hydroxide. And if we're looking for pH, since we have hydroxide, we can use that to find pOH by doing the negative log of 0.040. So our pOH is 1.40. But if this asked for pH, you would need to subtract from 14 to get a pH value of 12.60. And do be careful, because something I tend to see in the past is people will solve for pOH and think that they're done and not continue to solve for pH. So make sure that you are solving for the correct variable that you're looking for. That's something I have seen in the past. Let's look at what happens when we encounter this one. So here we have 50 milliliters of a 0.035 molar hydroiodic acid are added to 30 milliliters of a 0.049 molar sodium hydroxide. So hydroiodic acid is one of your strong acids. Sodium hydroxide is a strong base. So this is an example where we have the opposite solutions. We have an acid and a base. So we said for these, we still have to find moles of our ion for both of them. So the hydroiodic acid, its molarity times volume, so molarity is 0.035 molar, times our volume is 50 milliliters, so 0.050 liters. This is 0.00175 moles of hydrogen ions. For the sodium hydroxide, same thing, there's only one hydroxide. Our molarity is 0.049 molar. Our volume is 0.030 liters. When we multiply, that is going to be 0.00147 moles of hydroxide. And we said whenever you're doing opposite solutions, they cancel out. So you're going to subtract the smaller one from the larger one. So if we do the 0.00175 minus 0.00147, that means that what does not neutralize, what does not cancel out, is going to be 2.8 times 10 to the negative fourth moles of hydrogen ions, because that was what the higher amount was. So it's whichever one you have left over is what we're dealing with. So now that we know what moles do not neutralize, we said to find the new concentration, we have to divide by the total volume. So 50 milliliters and 30 milliliters is 80 milliliters, so 0.080 liters. That gives us a hydrogen ion concentration equal to 0.0035 molar. And if we're looking for pH, we can plug into negative log. And our pH is equal to 2.46. So since we did have excess hydrogen, we would expect this to be acidic. So that does match with our number value. Let's look at this one. This one we have 25 milliliters of a 0.050 molar barium hydroxide and 40 milliliters of a 0.051 molar nitric acid. Barium hydroxide is one of our strong bases. Nitric acid is one of our strong acids. So here we are going to be neutralizing because we have the opposite solutions. So same thing, we need to find moles of each one. So for barium hydroxide, looking at the hydroxide, there are two hydroxides. So we do have to multiply by 2. Our molarity is 0.050. Our volume is 25 milliliters, so 0.025 liters. That is going to be 0.025, or 0025, excuse me, moles of hydroxide. For nitric acid, we only have one hydrogen. Our concentration is 0.051 times our volume is 40 milliliters, so 0.040 liters. That is going to be 0.00204 moles of hydrogen ions. And here's where you don't want to necessarily round with each step, or it can skew your final answer. Because these are opposite solutions, we do have to subtract them. And remember, always do the higher one minus the lower one. So if we do the 0.0025 minus 0.00204, that is going to be 0.0005 approximately moles of hydroxide that is excess. So since we have hydroxide left over, we would expect this to be a basic pH, so higher than 7. To find our concentration, we divide by the total volume. So 25 milliliters and 40 milliliters is 65 milliliters. That gives us a hydroxide ion concentration equal to 0.0077 molar hydroxide. So that can plug into POH. So our POH value is 2.11. But if we're looking for pH, subtract from 14, and that will be 11.89. So remember, that is a basic pH value that is higher than 7. Let's look at this last one. And this will give you a clue how to approach some problems you may encounter. But for this one, it says to 50 milliliters of 0.010 molar nitric acid, 25 milliliters of 0.025 molar hydrocyanic acid is added. So looking at this, our nitric acid is a strong acid. Hydrocyanic acid is not on our list of strong acids, so this is a weak acid. Whenever you look at these, if you have a strong acid and a weak acid, you can essentially ignore the weak acid, and I'll do the math to show you why you can ignore that weak acid. And it deals with, because the weak acid does not ionize very much, it is not going to end up changing your hydrogen ion concentration whenever you combine the two together. So if we treat this the same way, where we are trying to find moles for both of them, and I do want you to kind of, we'll come back to in a second. So for nitric acid, if we do our molarity times volume, so 0.010 molar times 50 milliliters is 0.050 liters. This would be 5.0 times 10 to the negative fourth moles of hydrogen here. If we look at the hydrocyanic acid, that is a weak acid. So remember, weak acids don't ionize completely, so we are going to have to look at how much it ionizes. So with the hydrocyanic acid, when it is in water, remember, it gives up a hydrogen, so it will produce those cyanide ions and hydronium ions. If we initially have 0.025 molar hydrocyanic acid, we have none of the ions initially, our products are going to increase by a factor of X. Our reactant is going to decrease by a factor of X. So if we plug this into K, and like we said, you're typically going to be given Ka or Kb values when needed. Ka for hydrocyanic acid is 4.9 times 10 to the negative 10th. So whenever we're setting up our Ka formula, we have 4.9 times 10 to the negative 10th is we have x squared on top because of x times x. For our reactant, we can ignore x there because it's a large enough difference. So when we solve for x, we get that this is a concentration of 3.5 times 10 to the negative 6 molar. So that would be our concentration of our hydronium ions here, or our hydrogen ions here. In order to combine this with the moles of nitric acid, I would need to change this into moles. So it would be 3.5 times 10 to the negative 6. Sorry, I can't read my handwriting. Times the volume, where this is 25 milliliters, so 0.025 liters. That would be my moles of hydrogen from this one, which is going to end up being 8.75 times 10 to the negative 8th moles. Now, since these were both acids, we would typically add these together. So if we do the 5.0 times 10 to the negative 4th plus 8.75 times 10 to the negative 8th, that is going to be a total, when you look at sig figs, of 5.0 times 10 to the negative 4th moles, which if you look is the same as our number of moles from our strong acid. That is why I said if you're mixing a strong acid and a weak acid, you can essentially ignore the weak acid, because even after we did all that work, our number of moles for our hydrogen still matches the number of moles from the weak acid initially, or the strong acid initially, excuse me. So now that we have our number of moles of hydrogen, we divide by the total volume. So the 50 milliliters and 25 milliliters is 75 milliliters. That gives us a hydrogen ion concentration that is going to be equal to 0.0067 molar. And if we plug that into pH, it's the negative log of 0.0067. So our pH is going to be 2.18. So, like I said, you can ignore the molarity of that weak acid, but you cannot ignore the volume. So the overall volume does change. So the initial molarity of the strong acid changes because the volume has changed. So you do still have to find moles from your strong acid and divide that by the new volume, the total volume, and use that to find pH.